Okay, so I'm going to tell you right now a cool application of Green's theorem so that you see that it's useful for things that are not only directly related to the computation of work. Again, let me remind you the statement of Green's theorem. You have a vector field on the xy plane f that has components f1 and f2, and you want to compute the work. So you have a closed curve. You want to compute the work along this closed curve. And so what Green's theorem says is that rather than computing this work directly, you can compute instead a double integral where the region of integration corresponds to the region enclosed by the curve. And what you put inside the double integral is like this funny combination of partial derivatives. Okay? Now, the cool application is the fact, it comes from the fact that this vector field in more or less can be anything that you want. So let's say as an example that what happens if you take f to be let's see. So the idea is that at the point, let's think about it. You want the vector field at the point x comma y. I'm just cooking up this example. You'll see why in a moment. To be minus 1/2 yi plus 1/2 xj. In other words, at the point x comma y, the vector that you're going to draw is minus 1/2 y comma 1/2 x. So just to give you some idea of how this looks like, imagine that you have here x and y. So you draw one point, let's say this is the point 1 comma 2. According to my instructions, and here's a point 1 comma 2. According to the instructions, I'm going to draw a vector whose x component is minus 1/2 y. So it's y is 2 in this case. So the x component is -1, right? Let me just write it here. And the y component is 1/2 of x, so it's 1/2. And so this vector is something like this, right? This is points to the left because the x component is negative, and points upstairs to the north because the y component is positive. In fact, if you think of the position vector of this of 1, 2, it looks here that there is like a 90-degree angle between the two vectors, and it actually ends up being true in general, because if you take a point which is xy, okay, then let's see. Again, the vector that you're drawing is minus 1/2 y times 1/2 x. And notice the dot product between two vectors. If you want to know if two vectors are perpendicular, you compute their dot product. And if you do the dot product between xy and -1/2 y and 1/2 x, then you get minus xy over 2 plus xy over 2, and that's 0. So this f of xy is always perpendicular. It's perpendicular, it makes a 90-degree angle with the position vector xy. And in fact, the idea of this picture, what it should convey, is that somehow this is a vector field that's rotating. There's going to be some rotation or curl associated to this vector field. but that will become more clear in a couple of videos. And so this is a magical vector field that I came up with, or someone a long time ago. And what are the consequences of using this vector field? So let's apply Green's theorem to this vector field. Then you get that the line integral of f, which is minus 1/2 y, comma 1/2 x, dot b dt. This is not too important. This is just like the usual expression for our integrals. Equals, and now this is a cool part, equals the double integral of over r. What is the partial of f2 with respect to x? Well, the partial f2 is just 1/2 of x, so when you take the derivative of this with respect to x, you get 1/2. And the other one gives you minus 1/2. There's a minus here in the formula, so you get minus 1/2 dA. And so, what you get, again, along the curve, y is like a function of t. Well, let me just write it like this. You can, you can write it in many different ways, but let me just specify the fact that this depends on t. So what this is saying is that this integral over this curve of this quantity gives you 1/2 plus 1/2 is 1. So you're integrating dA. Integrating dA is just the area of the region. And again, this may look you have to think about this formula for a second just to realize how amazing it is. It is saying that the area of R, which is two-dimensional, can be obtained by doing an integral of some quantity on the exterior of R. Okay? So the information of a two-dimensional region can be completely determined by the information along the curve of some function. And in fact, there are two applications. A more modern application, I'll put a link to this on YouTube, is that like for example, for if you wanted to say know how much ice there is like on like Antarctica or North Pole, something like that, like how much ice is accumulated in some region, then you could use like a satellite and use Green's theorem to, instead of computing the double integral, right, you could compute like an integral along the boundary of the region that where you wanted to compute like the total mass of ice containing it. Or there's like a thing that people use in the past, which, well, I bought it on eBay. I don't know if there's still toys. I mean, I don't know if you can still buy this, but I'll give a link to the YouTube video. So there's a thing called the planimeter, which I'll just show you a piece of it. It has two pieces, you have to set it up. But a point of a planimeter is that it's something that it's like a machine that people would actually use back in the good old days to compute the area of a region like this by just moving around like something along the curve. And the planimeter will start changing the numbers and give you the total area. So again, like my explanation is not very good, but there's a thing called the planimeter, which literally computes the area using this method, like just by moving along the curve. And I'll give you the link in case you want to watch it. But so let's put this in practice. so that you see how this works out. So let's find the area of the ellipse. The position vector of an ellipse is a cosine of t, b sine of t for t between 0 and 2 pi. So when a and b are both the same, that's the equation of a circle of radius a. And when a and b are different, you just get an ellipse. So here's a way to find the area of an ellipse using Green's theorem. And according to Green's theorem, the area, well, is an integral over the ellipse. So here's the ellipse. And so the area would be the integral over this curve. The curve goes from 0 to 2 pi, because that's the time that I gave you, of minus 1 half y of t. Y of t is b sine of t. 1 half x of t, which is 1 half a cosine of t. And that's dot product with the velocity. The velocity of this vector is minus a cosine of t, minus a sine of t, b cosine of t, dt. And so we have to integrate from 0 to 2 pi. You get, let's see, minus with minus gives you plus, so you get ab sine of t cosine of t over 2 plus ab sine of t cosine of, sine square of t, right? Sine gives you sine square, and then ab cosine square of t over 2, that's dt. And so that's just cosine squared plus sine squared equals 1, so you just get the integral from 0 to 2 pi of ab. Let's see, dt. Okay. Oh, yeah. I should not be so. Let's factorize ab over 2, so you get sine squared plus cosine squared dt. Sorry. This is 1, so you get the integral from 0 to 2 pi of ab over 2, and this is just pi ab. So again, when a equals b, you get a circle of radius a, which is pi a squared, the area, which is what we know. And so this is a generalization for the formula of the area of a circle. But notice that we did not use a double integral at any point. We only use an integral over the boundary of the ellipse. Or not we didn't integrate over the interior of the ellipse. We just had to use a boundary.